Hi all, this is Mr. Yeager with AP Physics. This has been the first video in a while that I've made, but we have a new unit in AP Physics with fluids. So we got some new videos out here. So I'm thinking I'm going to be splitting this up into probably about 3 videos, this unit. The nice thing with this is a great unit after finishing up energy, depending on where you are with this, with your course, because we basically are going to repeat many of the concepts in terms of force, in terms of energy, in this unit with fluids and the laws and the different situations you're going to be presented with. So as long as we can kind of see that it still falls under these particular umbrellas of force and Newton's laws and energy, we shouldn't be looking at this as something that is completely foreign and new and unique to like a standalone unit. It is not in the end. So here we go. You can see the water flow in there. It looks amazing. Okay, so what's going to be covered? We're going to be looking at density and states of matter, which is very much a kind of a review of some chemistry topics. You'll see again from gas laws and again learning states of matter in chemistry. A lot of that stuff is obviously what's going to be continued in this unit with physics, just obviously manipulating it a little bit differently. We're going to look at fluid statics. We're going to look at fluid dynamics. Again, very common, just like we did with forces a lot of times, is we did static forces and then dynamic forces. We're going to do it with rotation, where we're going to look at rotational, like static equilibrium with rotation, and then dynamic. All right, so it's a great way to kind of separate out these situations so you can kind of focus on how to approach them. And then we're going to bring in conservation laws, okay, like conservation of energy and conservation of mass. Okay, so a couple measurements that we're going to be using a bit more of that we haven't used so much yet is volume. Okay, again, we're talking about a liquid here, so we need to know the amount of space it's going to take up. We're going to be interested in submerging objects, and that's going to be a big part about determining how much. Obviously, if you submerge something, it's going to take up space, and there's going to be a very strong correlation between the amount of space taken up and the amount of space displaced. They should be equal. We will be using the unit meters cubed for volume, not milliliters, not really liters, not you might see centimeters cubed occasionally. Okay, those are all ones that we primarily use back in chemistry because you're usually talking about small amounts. In this unit, and the situations we're going to give, we are going to be talking about large volumes of water. We're going to be talking about like lakes and giant, water tanks that you see around town and things like that in terms of, covering huge amounts of water that are taking place. The other unit we'll be using or measurement is density. Okay, we have not used this one at all. The symbol for it is this rho symbol, okay, which does look like a P. So be careful with this and momentum, the P for momentum. All right, this is rho. Density is mass divided by volume. Again, something we should already know coming from chemistry many times, okay, maybe from biology, whatever. All right, so density again is specific to a particular substance. It is something that we can use to identify the substance like we learned in chemistry, so it is something that should stay constant when we're talking about solids and liquids. Okay? We will be measuring density in kilograms per meter squared, again using large units of it. This is also good because in all our formulas we like to be in kilograms and we like to be in meters when we try to apply any formula in physics. One of the things that we should try to remember and try to memorize is water will have a density of 1,000 kilograms per meter cubed. Okay, so that's something that we should be able to measure out. Sometimes some teachers will do labs to kind of determine that from tap water, which again might be slightly different because it's not completely pure. Okay. All right, properties of states of matter. So we know we have liquids, solids, and gases. Okay, we've primarily been focusing on solids so far throughout, and we will go back to it primarily. Again, this unit is really the only one that we're going to be looking at a different state of matter that we're manipulating. All right, solids, everything's pretty straightforward. You can't manipulate it. Everything is constant: mass, volume, density, and shape. You're not going to be able to change it. Okay, liquids. Mass, volume, and density, the three measurements will all be constant, okay, when we have this problem. Obviously, we could possibly alter what the volume is, but when we do that, we alter the mass, but the density stays the same. But the nice thing is they will stay consistent. The only thing that will change is the shape of it, okay? Obviously, we'll get to that with pipes and other things that obviously the water goes through, okay? We can manipulate the shape. Now, I want to be clear right now, we don't compress a liquid, okay? That is not what we're meaning when we're changing the shape, okay? The particles cannot get any closer, okay? They're already really close together in a liquid, but the particles are loose enough that they can flow around each other and they can manipulate their shape. Gases, on the other hand, at the other side, they do have a constant mass, so we're going to talk about a particular amount, but you can manipulate their volume, density, and shape because there is so much space in between the particles. Okay, so that is a little bit tougher to mess around with. Gases, again, are fluids because they can move on their own, all right, just like liquids, but we're primarily focusing on liquids. So I already stated this in the last part. Liquids, we're going to be able to manipulate what they look like, and so they kind of, again, I could use the word squeeze, but again, I'm not compressing them, all right, through the pipes, tubes, other things, but we're going to do that with a constant density and a constant volume of water, therefore a constant mass, okay? So the mass where it is at the beginning is going to be the mass the same at the end, all right, if it's flowing through a closed tube. All right, moving into some fluid statics, okay? Basically situations where we have a fluid and I'm going to be interested in floating objects. I'm interested in maybe something that's hydraulic, a hydraulic machine, okay, where the fluid stays in basically place, but might be again changing the size of the tube that it's in. All right, submersing objects, etc. So we're going to be looking at pressure, Archimedes' principle, and determining density through this situation. Again, we have a formula for density. We will kind of see that sprinkled in here and there. I think during the rest of this video, I'm going to focus on that pressure part because that is a new unit. So, pressure. Pressure, the formula is force over area, okay? Force over area, F over A. The unit for it, and you're going to see in a moment, there's lots of units for it. The unit we will primarily be using for it is newtons over meters squared, okay? Force over an area. And this is equal to what we call a Pascal, a PA. So 1 Newton meter squared is a Pascal. They are equivalent units. Pressure is also a scalar, okay? So we will not give the pressure a direction to it, all right? The force has a direction, but the pressure does not. It's a force is acting over the area, and we just say this is the amount of pressure acting on the object. So, jumping into an immediate problem with this, okay? Kind of already looking at this formula and how this might be manipulated early on. High heels are notorious for creating cracks in hardwood floors, in tile floors, basically these very, very hard floors that we wouldn't think, that feel like they should be resistant to things, but they will crack, okay? And so why will high heels generally cause cracks more often than, let's say, sneakers, okay? So we're basically looking at a comparison. Why will sneakers not cause cracks? Why will high heels cause cracks? So what we're basically looking at here is, pretend we have a person, okay, and they're wearing sneakers, okay? So if they wear sneakers, okay, and I'm going to just draw like that. That's my sneaker. Looks like I don't know, it's just a circle. All right, but we got a sneaker there. Okay, it's like a slipper. And what we have is, obviously, if they're pushing down on the floor with this slipper, okay, they're going to be pushing down with their gravitational force, their weight, okay? If they're in their high heel, I'm not going to even try to do a high heel, okay? If they're trying to do a high heel, I'm going to circle this part down here, okay? Yes, they're applying a force over here as well, but the weight is still pushing down through the high heel. The weight that you're applying with your sneaker and the weight that you're applying with your high heel are the same. But what am I manipulating? It's the area, The area, especially at the heel, is much, much smaller than it is for a sneaker. So if I have the same amount of gravitational force, but I decrease my area, I increase my pressure. If I decrease the area, I increase my pressure. There's an inverse relation between the two. And due to this increase in pressure acting on this one spot of the floor, this can cause tiles, hardwood floors to crack. Okay? So it's just manipulating that variable a little bit between the two of them. Okay, so let's talk about liquids though. With liquids, what would be my formula for pressure with a liquid? Okay, it would still be force over area, but we're going to modify this. Okay, we're going to bring in density, volume, things like that we would use with it. Okay, that we'd be given. So we're going to look at this, and again, this should be gravitational force. The gravitational force, the force that the liquid's applying, and again, I'm just basically saying you have a liquid in a container, okay? What's the pressure at the bottom versus maybe somewhere else, okay? As you know, when you dive down into water, there's greater and greater pressure on your ears. Why is that, okay? So it has to do with the amount of water that's above you, okay? So we can figure out, obviously, the gravitational force of that water. How much water is pushing down on top of you, okay? But we're going to bring in density, because many times we'll know the density of the liquid that the object's in, or that you are, well, hopefully you're only swimming in water, but whatever, okay? So I'm going to replace F with mg, okay? But I'm also then going to replace m. So m is equal to the density times the volume. So that's where I'm getting this rho v. Okay, so I'm replacing m with rho v, the density of the fluid, the volume of the fluid, okay, times g over the area that the liquid is taking up. But I'm going to simplify this even more, okay, because volume is length times width times height, okay, or area times height. Yes, you could technically be like, length times height, is the area times the width, but we're not going to get silly with it. We're going to say area is length times width, and then you add in the height. So I'm going to plug in AH for V. And what do I get? I get rho AHG over A. So what happens to the areas? They cancel out. And so the pressure that you feel in a liquid, okay, is equal to the density of that liquid times gravity times the height. And again, when we say height, we're talking about, you can say height or depth. How far down are you, or how much water is above you? What height of water is above you is the pressure you feel by that liquid. Okay? All right, I know we kind of are jumping straight to this, but that's because we're going to have to apply these in not separate situations, but all together. So another pressure I need to bring in is what's called standard atmospheric pressure, okay? This is the pressure due to the Earth. And we say the Earth has an atmosphere, so we have quantified that as the standard atmospheric pressure is 1 ATM, 1 atmosphere. ATM is atmospheres, the unit atmospheres. All right? Well, 1 atmosphere equals 1.013 times 10 to the 5th Newton meter squared, which you might have learned back in chemistry if you had to do some of these conversions. We often did 1 ATM is 101.325 kPa, kilopascals. Okay? What we will do is we're going to primarily use this idea and use another unit. I know it's like, why did you introduce those? Is we have something called the bar, okay? The pressure unit bar. And 1 bar, we kind of simplify this down, is basically 1.00 times 10 to the 5th Newton meter squared, which is 100,000 Newton meter squared, is 1 bar. That will be our primary standard atmospheric pressure given to you in physics. Okay, it's 100,000. So the thing is, you have that, and then we have something else called gauge pressure. Okay, and this is why you have the tire to the side. This is the pressure that if you actually, if you wanted to figure out the pressure in your tire, okay, you put this gauge up to it. If you've been to a place, any tire place, where you have them fill up your tires or whatever, they have that gauge that tells them how much pressure is inside the tire. That is just measuring the pressure inside the tire, okay? All right, just from that device, how much pressure is created from the tire inside the device. The thing is, what we have is we have what's called absolute pressure. The gauge pressure is only looking at the pressure inside the actual object. It is not bringing in the standard atmospheric pressure. So this is where absolute pressure, which I know we just labeled P, and this is where it gets a little confusing, is equal to the atmospheric pressure. So what's happening is there's way more pressure on this tire than just what's inside the tire. Okay? You have the atmosphere pushing on that tire as well, and so the total pressure that's on those particles inside that tire is the combination of the two of them. Okay? So we often will see this as P equals P naught plus rho GH when we're dealing with fluids. Okay? Because this is the pressure within the fluid plus the additional pressure that's pushing down on the fluid from the atmosphere itself. So it's a combination of the two. Okay, and so that's what I have there. So we'll often substitute this in, and there you go. This is the official formula to basically figure out the pressure of an object underneath water. All right? So that's the thing. When you're above water, you still have quite a bit of pressure. You have the atmospheric pressure on you. When you dive underwater, and this is where it can hurt, obviously, as you dive deeper and deeper down, the pressure on your ears, on your entire body, increases based on the depth that you go. And this is also why, obviously, when you come back up, the pressure should be decreasing, and you've got to be careful with that. Okay, that's where we get a condition called the bends, which I'm not going to get into, but is something that scuba divers can run into, or free divers can run into if they rise out of water too fast. Okay? All right. One more principle, I believe, that I want to share is what's called Pascal's principle. And what this is basically trying to illustrate is that if you have a closed system, okay, with a fluid in it, okay, you do have a fluid in it, the force out over the area of where the force is coming out is equal to the force in over the area in. And this is where we get hydraulic machines or brakes, okay? You pushing that brake down is not really what's going to make the car stop. That little bit of pressure that you create pushing it, that brake inside your car is not actually what's causing, is not directly causing the car to stop. What happens is those brakes work through a hydraulic system. This is why you have braking fluid, and it acts on a much smaller area, and therefore quite a bit increases that amount that you put in, okay, basically. So we have this, there's a big change in the two of them in order for them to have, sorry, let me say that again, is basically, you've put that force in a small area, but if you increase the area, the force has to increase as well. And that's what we have here. So that's what you see even with lifting cars at, obviously, again, tire places and such. A hydraulic machine, you can put that little bit of force in and then obviously create a great force out over the same area because the pressure has to be the same everywhere. Okay? That's Pascal's principle. Sorry, a little bit misworded there. All right, so last thing for this this video I want to share is just I want to bring in this PhET sim. So again, this is from the University of Colorado, this PhET sim. And all I wanted to show is, again, the idea of the pressure increasing as you go down. So I like this because you can see the pressure is atmospheric pressure when you're not in the water. And then as you go into the water, the pressure is increasing. Okay? And we can figure out the pressure of the fluid. We subtract out the 101.325 kPa of the atmosphere, and that would be the pressure underneath the fluid. So again, as I increase H, I'm increasing pressure. Okay? If I decrease H, I decrease pressure. So that's all I again, This could be if I change the density of the fluid, obviously that would increase the pressure. If I change the gravity, that would increase the pressure because those are also part of my formulas. All right, so that's what I'm going to leave you with today. We covered the introduction to fluids, the idea of pressure primarily, and the pressure created by a fluid. So there you go. Thank you.